humans are quite clever, but when it comes to area, we don't really know an awful lot. I always say that the only thing we know how to find the area of is a rectangle. Our ways of working out the area of a parallelogram, a trapezium, a triangle are all based around turning it into a rectangle, and even a circle. The definition of the area of a circle comes from breaking it up into sectors, rearranging those sectors into a rectangle. And so when we come to work out the area under a curve like this, which is a problem that had sort of, had interested mathematicians for many, 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 many years, all we can really do is say, okay, let's say I want to find the area from here to here. Well, let's break it up into little rectangles. Okay, they should all be the same width, but there we go. So I'm breaking it up into rectangles. There we go. And the area of that rectangle is going to be, well, this height is the y value at that value of x. So the area is going to be equal to the y value multiplied by how wide that is. So we say delta x, don't we? Is there sort of a change in x? And I'm going to turn that d into a delta. So that's the area of each of these rectangles, the y value of the function at that point multiplied by the width of the rectangle itself. So what we need to do is we need to add up all those rectangles in between this value, and that's not a particularly good estimate for the area. So the question is, how do we make it a better estimate? And of course the answer is that we make the rectangles narrower and narrower and narrower. So we reduce this width until it's so small that it's nothing at all. And you might think, well, do you know what, that rings a bell. That rings a bell because recently when we learned how to differentiate, we differentiated, which is of course about finding the gradient of the curve at a particular point. We did it by saying, okay, so that's my x value, and this height is the value of y at that point. Let's go forward a little bit further. And I want to know the gradient of the curve at this point. Well, that chord joining those 2 points is a pretty good estimate to the gradient of the curve at that point there. So we turn it into a rectangle, and we say, okay, so this is this is a change in x, delta x, again that should be a delta, and this is a change in y, so the gradient is the change in y over the change in x. And it's not a very good estimate actually. If you draw a tangent at this point and compare it with the gradient of that chord, it's not very good. How do we make it a better estimate? Well, we reduce this value, the distance that we go to draw the chord. We reduce it so it's so small that it's absolutely nothing. And so these two techniques are very, very similar. The whole idea of finding the gradient of a curve by drawing this chord and making this distance so small that it's barely nothing, and finding the area under a curve by finding the area of lots of rectangles but making the width of those rectangles so small that it's barely anything. These processes are very small, and it was in the 17th century when two mathematicians in particular realised the similarity here and formalised what we now call calculus. And those two mathematicians were Newton and Leibniz. The amazing thing is that the techniques that we use to find the gradient of a curve, which you've learned how to do recently, it's the inverse operation that we do to find the area under a curve. And it was Leibniz that first adopted a notation that says, okay, the sum of lots and lots of rectangles like this can be found by the reverse of differentiation, which we call integration. And it's quite easy to show how this method gives us the method of differentiation that we use to multiply by the power, reduce the power by 1. And so differentiation from first principles is on the A-level syllabus. It's harder to show that the sum of lots of rectangles of a tiny, tiny, tiny width can be achieved by doing the opposite of differentiation, which we call integration, whereby we increase the power by 1 and divide by the new power. But it is true. So these two principles, these two techniques, one which you've already learnt, differentiation, and one which you will learn shortly, integration, they're inverse operations, and they both form the this area of math called calculus, which is about how things change. So we've got the gradient of a graph changing, we've got the area under a curve changing as x increases. And it's worth going onto YouTube and looking up the whole Newton-Leibniz thing, because they claimed to have developed the same thing independently, and there is all sorts of debate about who came up with it first. The Greeks were the first people to use this whole idea of taking something and then making either the width very, very small or the jump very, very small. But yeah, there's a lot of stuff on YouTube about it, and there was an unseemly spat really in the 17th century, in the 1600s, when Newton and Leibniz were scrapping over who came up with the idea. But there we go. You can look that up in your own time. Right. So you know how to differentiate. So you know to find the gradient of this curve, y equals 2x cubed, when x is 1. You multiply by the power, so 3 times 2 is 6, and you reduce the power by 1. And that gives you a formula for the gradient at any value of x. So when x is 1, dy by dx is 6 times 1 squared, 6. So we know the gradient of the curve at that point is 6. So how does the reverse process work? So let's say we want to work out the area under the same curve between 1 and 3. So the notation which sort of Leibniz came up with, although it sort of has developed over the years, is we say, okay, now the delta x has become dx, and what that's saying is that x is the variable. So if this is an expression with maybe pi or a or b in it, we are saying x is the variable, so pi and a and b, they're constants. So this is the notation that says I want to work out the area under this curve between 1 and 3. So remember, when we differentiate, we multiply by the power, reduce the power by 1. So we are going to increase the power and divide by that new power. Now there's a bit of a problem at this point, which we have to address. If I wanted to differentiate, if I wanted to differentiate that, and if I wanted to differentiate that, and if I wanted to differentiate that, they'd all have the same answer, wouldn't they? They would all be 6x squared. This would be 6x squared because when you differentiate a constant it disappears, and this would be 6x squared because when you differentiate a constant it disappears. So if I want to integrate 6x squared, how do I know whether it was this, this, or this? And the fact is we don't know. We don't know. So what we do is we just have to say, okay, potentially there's some constant there. So we've integrated, we've done the reverse process, and now all we need to do, like when we differentiate, we substitute the value of x in, we now need to substitute the values of x in at 1 and 3. And it's a slight simplification, but 1 will give you the gradient up to that point, and 3 will give you the gradient up to that point. So if we want to have the gradient in between, we substitute 3, and then we take away what you get when you substitute 1. Now it's a little bit more complicated than that. not least because areas under a curve, areas under the x-axis appear as negative. So you've got to be a little bit careful, but this one's fairly straightforward. So I'm a bit notation crazed about this, so I tend to do it like that. And so I've got, oh, and sorry, I should have simplified this, shouldn't I? So that's x to the power 4 over 2. So this 3 to the power 4 is 81, so that's 81 over 2 plus c. And over here I've got a half plus c. And of course the great thing there is that you've got 81 over 2 take away a half, so that's going to be 40. And you've got c take away c, so the constants disappear. So we know that the area there under that curve is equal to 40. No units, because it's on a graph, so it's just sort of 40 square units, and you wouldn't be expected to give a unit at all. So just as a practice, have a go at doing this one, x cubed plus 2x squared minus 2, and see if you can find the area under that curve between 1 and 2. Pause the video at this point and I'll show the answer in just a second. Okay, so increase the power, divide by the new power, increase the power, divide by the new power, minus 2. So you've just got to think this is the opposite of differentiating. So if you differentiate minus 2x, you get minus 2. So that's that. Then I substitute the values in. You've got a negative value here. Remember we talked about it being not quite as straightforward. But yeah, that's there must be some area under the curve at some point between 0 and 1. You can have a look on Desmos to see that. So you end up with 16 over 3 minus 13 over 12. So it's 16 over 3 plus that, which gives you that. Now a quick, and forgive me if this is patronising, but the way I do this on a calculator when I'm trying to substitute values in so I want to substitute 2 in first, so I do 2 arrow x like that, and then I type in this. So that's x4 over 4 plus 2x cubed over 3 minus 2x. Don't bother with the c because we just know the c's are going to disappear, and it does it for me. But here's the clever bit, and forgive me if you've already worked this out. If you go up here and you just delete the 2 and turn it into a 1, it re-evaluates it with that value there. So there we go. Now you can get your calculator to work out the answer for you. Your calculator won't do integration. Your calculator's not allowed to do algebraic manipulation, but it will if you press the what did I press? The math button, and then go to the second page. It will let you check integrations. So I'm going to type in the original question here. So x over 3 plus 2x squared minus 2, and then you press sort of right, it gets you to this value here. So that's from 1 to 2. It gives you the answer. Now you're not allowed to use that to work it out, but you can use that to check. Okay. Right, now let's say trying to find my vase. Yeah, there you go. So let's say that I want to work out the volume. Sorry, it's late and it's not really light in this room, so I apologise about the funny light. So I want to work out the volume of my beautiful vase, the volume of my vase. So what I can do is I can say, okay, let's work out what the equation of that edge profile is. So let's say it's x squared over 12 plus 4. And then what I'm going to do is take that profile and I'm going to rotate it around the axis 360 degrees. And just like we can work out the area under a curve by breaking it up into rectangles, I can work out the volume of this shape by breaking it up into lots of cylinders. Now the volume of a cylinder is pi r squared h, and normally, you know, you're talking about a cylinder that's sort of this way up, so that's h and that's r. But what we've got here is a sort of cylinder lying on its side, so the radius of that cylinder is the y value, isn't it? So you've got pi y squared multiplied by the height, which is this however wide our cylinders are going to be. So that's delta x. And so what we can show, and you know, I'm not going to sort of do the full proof, but let's say we want to work out the volume from 0, say my vase is, I don't know, 8 centimeters tall, so 0 to 8, it's the integral of pi times y squared with respect to x. X is the variable. And because pi is a constant, constants aren't involved in integration at all. They're, you know, it's a coefficient effectively, and it's just going to pass through unchanged. So I'm going to put that out here. Now I mustn't forget about it, but it just makes it a whole lot easier when I'm integrating. So this is how we use integration to find a volume. It's called the volume of revolution, and it's the thing that's on our syllabus. Now, okay, this is a slightly complicated volume, so let's start with something a little bit easier. So let's say we want to find the volume of this function on its own if it's rotated around the curve. So this isn't so much of a vase, more of a sort of a, I don't know, a party hat. And it's a party hat which is 8 centimeters high. So what we're going to do is we're going to integrate pi y squared between 0 and 8 with x as our variable. So this is what y is. So y squared will be x to the power of 4 over 144. So go on, pause the video, see if you can integrate that. Don't forget at the end you've got to multiply your answer by pi, but leave that until right at the end, and yeah, have a go. Pause the video at this point. Okay, so here we go. So I'm going to whack the pi there. So the integral of, that's a bit slightly large at this point, never mind. So I'm going to increase the power and divide by the new power. Now I've already got 144 on the bottom, so if I divide by 144 and then divide by 5, I'm embarrassed to say I am doing 144 times 5 with my calculator. That's now, yeah, I regret the curly brackets, so I'm just gonna put a pi out the front there. You'll notice I put plus c here, but I don't bother putting plus c when I substitute the values in. So here we go. So it's pi times so that's going to be, it's nice and easy, that's going to be 0 when x is 0, and when x is 8, so I'm going to go 8 arrow x, and it's going to be a big number, isn't it? X to the power of 5 over 720. Ooh. So this time perhaps I don't know, perhaps I ought to have some brackets there. So my answer is 2048 over 45 pi. Again, don't tend to have units unless it's a question with a particular context. Okay, so I suggest you have a look on in the CorePeer book, page 73. Question 1 is just a few little warm-up ones. Question 2 is quite an interesting question because it's a volume of revolution, but they don't give you this value here. So you've got to work out where this curve crosses the x-axis. Hopefully you've got strategy up your sleeve to do that. But then you've got to rotate it, and so you need to square this. So that's a fairly complex sort of calculation, isn't it? But yeah, have a go. You'll notice that question 1 talks about rotating at 360. Question 2 talks about rotating at 2 pi radians. It makes no difference. It's the same principle. And if I've completely confused you, then page 72 goes through the whole volume thing, although it assumes that you already know how to integrate. Right, so that's part 1. And I'll try and do the other 2 parts in a subsequent video later this week. Hope you're all okay. See you soon. Bye bye.